Hello and welcome to your first online lecture for Calculus 3, Multivariable Calculus. This is on chapters 13.1 to 13.2 of the textbook. Usually these will be on just a single section, but both of these sections are very short, and I felt it better to combine them because of their very unified topics. So, chapters 13.1 to 13.2 are on vectors, and in fact, all of chapter 13 does not get into calculus. We begin calculus in chapter 14, and multivariable calculus fundamentally involves calculus in 3 dimensions, and later on in the course, vector calculus. And we can't do calculus in 3 dimensions, let alone vector calculus, if we don't know how 3 dimensions work, how to visualize equations in 3 dimensions, what vectors are. So chapter 13 is dedicated to that. These are examples in 2 dimensions, but vectors can be in 3 dimensions as well. A vector has a tail, which will typically be the origin, that is the point 0, 0, and it goes out to another point Q. It's directed in that way, and that point is called the head. So this is the vector PQ, going from point P to point Q, and we typically denote vectors with this arrow, or half arrow in this case, over the vector. And 2 vectors u and v are said to be equal if they have the same length and same direction. So a vector is, in this sense, a length plus direction. By custom, vectors are usually represented with the tail at the origin and head at some specified coordinate. And a vector with its tail at the origin is said to be in standard position, also called a position vector. And one way of denoting vectors is with these brackets and the head of the vector specified, and we specify that head with coordinates in Cartesian coordinates. So for example, this vector 2, 3 is a position vector that goes from the origin 0 to the point 2, 3. So the point 2, 3 is this point. That's 2, 3, 2 in the x-axis and 3 on the y-axis. And the vector corresponding to that in standard position is that vector. And an equivalent way of writing the vector v1, v2, where this is our x-coordinate, that's our y-coordinate, is v1i plus v2j. So that I denotes the magnitude in the x direction, the j denotes the magnitude in the y direction. And later, once we get into 3 dimensions, we'll also have a k for denoting the magnitude in the z direction. So these 2 are 2 equivalent ways of denoting the vector 3, 4. 3, 4 is 3i plus 4j, and we can visualize that as moving 3i in the x direction, 3 in the x direction, and 4 in the y direction. And vectors can be added together, which we'll get to in a bit, and multiplied. And one type of multiplication will actually encounter 3 types of multiplication, but the simplest type of multiplication is scalar multiplication. Scalar multiplication is a vector times a real number, in this case denoted a, and very simply, a times x comma y is ax to ay. So we just distribute that a as scaling both coordinates of the vector. And graphically, this corresponds to stretching the vector by the factor a. So for example, imagine this vector v. 1/2 v is that vector stretched by a factor of 1/2, which means 1/2 the length, but still in the same direction. 3v is taking that vector v and stretching it by a factor of v. And by the way, why does this correspond to multiplying both coordinates of the vector by a? Well, if we imagine that this is the x-coordinate and that's the y-coordinate, then in this case, when it's stretched by the factor of 3, then now this length here is 3x, and this length here is 3y. And if you multiply by a negative number, then that means that the x-coordinate is now negative 2x, and the y-coordinate is now negative 2y. So the vector is facing in the opposite direction, and in this case is of length 2. And 0 is odd. This is a mathematician's joke because 0 is an even number, but we're using odd in the sense of unusual. So the 0 vector 0, 0, denoted more generally by a bold 0 or 0 with the vector arrow over it to specify that it's the vector 0 and not the number 0, is the only vector whose length is 0, and also the only vector that does not have a direction. It's kind of just a point. It's going from a place to itself. And definition, two vectors are parallel if one is a scalar multiple of the other. That is, vectors v and w are parallel if v is equal to cw for some scalar c, or w is equal to cv for some scalar c. And we can imagine this, let's visualize this. Here is a vector v, and here is a vector, say, w. Pretend that those are completely parallel. And in this case, w is twice the length of v, so w is 2v. And this means that the 0 vector is technically parallel to every vector, since 0 times v is 0 for every vector v. Distributing the 0 to all coordinates, every coordinate becomes 0. And we'll see later that the 0 vector is also perpendicular to every vector, including itself, which is odd sounding, and indeed 0 is odd. So in addition to scalar multiplication, vectors can be added together. And adding two vectors together is just a matter of adding their respective coordinates. So x1, y1 plus x2, y2, adding together the x coordinates, we have x1 plus x2, and adding together the y coordinates, we have y1 plus y2. And how we really want to think about this is graphically. So graphically, to add u and v in this case, what we do is take one of the vectors, say v, and we translate it over so that its tail is at the head of u. And that's what the second diagram here illustrates. And then u plus v is the vector going from the tail of u to the head of our new translated over v vector. And why does this correspond to this algebraic definition of vector addition? Well, if we imagine, so here's u, it has coordinates, say, x1, y1, and here's v, it has coordinates x2 and y2, then the coordinates of u plus v, well, this is x1 plus x2, so that's x1 plus x2 in length. And similarly, this length here is, as you can see, y1 plus y2. And in this case, we translated v over to be so that its tail is at the head of u, but we could equally well translate u over so that its tail is at the head of v. And that's what this third diagram illustrates. And in fact, it forms a parallelogram, and u plus v is this diagonal of the parallelogram. And indeed, vector addition is what we call commutative. U plus v is the same as v plus u. The word commutative means that you can swap the order and you get the same result. So again, this geometric way of thinking about vector addition is really how we want to think about it. The algebraic way is how we compute it, but it's not very meaningful in terms of understanding what it means. Now, why do we care about vector addition? We'll see many ways in which we care, but perhaps the simplest is this nice little illuminating example. So here is a plane, and say the plane wants to travel horizontally. Well, the plane, if there's a wind velocity, w, then the plane needs to go in some sense against the wind, and going against the wind will make it turn out to go horizontally. And the velocity of the plane relative to the air plus the velocity of the wind, that's geometric vector addition, will be in total the velocity of the plane. So in this case, if the planets, my goodness, if the plane velocity relative to the air is 500, 130, which means that for every hour it travels 500 miles east, then it travels 130 miles north, and that's in the absence of any wind. And the velocity of the wind is 50, comma, minus 130. Then the plane's ultimate velocity is adding together the two x coordinates. 500 plus 50 is 550, and 130 plus negative 130 is 0. And that corresponds to going 550 miles per hour in the x direction and 0 miles per hour in the y direction, i.e. horizontal. And vector subtraction is really just vector addition. U minus v is u plus negative v. So in this sense, the way to compute u minus v, well, negative v has the same magnitude v, but is flipped in the opposite direction. So u minus v is u plus negative v, there's u minus v. And algebraically, we should note that x1, y1 minus x2, y2, well, that's the same as x1, y1 plus negative 1 times x2, y2. And then distributing this minus 1 to both coordinates, that's the same as x1, y1 plus negative x2, negative y2. And, well, that's the same as this. We have x1 plus negative x2 is x1 minus x2, and y1 plus negative y2 is y1 minus y2. So that's the formal definition from vector addition and scalar multiplication of why vector subtraction is just subtracting the corresponding coordinates. Now, we talked about how a vector is a direction plus a magnitude. And what is the magnitude of a vector in terms of its arithmetic coordinates? Well, a vector going from a point x1, y1 to the point x2, y2 is x2 minus x1, comma, y2 minus y1. And this demonstrates that visually. Its x-coordinate is x2 minus x1, and its y-coordinate is y2 minus y1. And we denote the magnitude of a vector with these absolute value signs around the vector. After all, the absolute value of even a number is the magnitude of its position vector from the origin. Let me illustrate what I mean. So here's our number line. There's 1, 2, there's negative 1, negative 2. And we can imagine the number negative 2 as that vector. We can imagine the number 2 as that vector. So that's the negative 2 vector, and that's the positive 2 vector. And the absolute value of the negative 2 vector is 2, in the same way that the absolute value of negative 2 is 2. So the use of the absolute value sign here is appropriate, and it generalizes the absolute value on the ordinary real number line when we think of numbers as one-dimensional vectors. Anyway, what is the magnitude of a vector in terms of its coordinates? Well, it's the length of this hypotenuse of the triangle, and we know how to find the hypotenuse of a triangle using the Pythagorean theorem. The Pythagorean theorem says that if we have a right triangle with side lengths A, B, and C, here's a right triangle with side lengths A, B, and C, then we know that A squared plus B squared is C squared, and taking the square root of both sides, this hypotenuse C is the square root of A squared plus B squared. So that's all this definition of the magnitude of a vector is saying. It's the square root of one side of the triangle squared plus the other side of the triangle squared. Now, linear combinations of vectors. A linear combination of vectors v1, v2, v3 is an expression of the form c1, v1 plus c2, v2 plus c3, v3, where scalars c1, c2, and c3. And this generalizes, we can have plus c4, v4, etc. But for the sake of simplicity here, I'm illustrating only 3 vectors. And these are some visualizations of linear combinations. So if we have vectors v and w denoted here, then we can imagine getting to various points, in this case, P, R, and Q, as linear combinations of V and W. So for example, to get to the point P, we want to go 3 in the V direction and then go 2 in the W direction. And therefore P is 3V plus 2W, and that's C1V1 plus C2V2 using our general notation. So look at what we have. This looks like a coordinate system. And indeed, it is a coordinate system generated by those two vectors. And the weights, as we call them, the C1, C2, on the vectors to get to various points are the coordinates in this coordinate system generated by those vectors. And this fundamentally is why linear combinations will be important. So here is the thing that we just drew up here. And similarly, to get to this point Q, we go 3 in the V direction and -1 in the W direction. That illustrates this. And we can decompose vectors. So given a vector A consisting of where we only know its direction and magnitude, how do we get back the corresponding X and Y coordinates of the vector? Well, we use trigonometry. So if we have a vector here of length A, then the X coordinate is A times the cosine of theta, since the cosine is adjacent over hypotenuse, and adjacent over hypotenuse times hypotenuse gets you adjacent. Let me write that out. Cosine of theta is adjacent over hypotenuse, as you'll recall from trigonometry, and therefore A times cosine of theta. Well, A is the length of the hypotenuse, cosine theta is still adjacent over hypotenuse, and those cancel out, and we get back the length of the adjacent, in this case, the X coordinate. And likewise for the Y coordinate. Y is the hypotenuse times the opposite over hypotenuse. And decomposing vectors like this will be necessary to add them together using our algebraic definition of vector addition, adding the corresponding coordinates. Okay, so here's an intimidating looking diagram of adding two vectors A and B together, where for both A and B, we only know their directions. And by the way, the directions were given by this angle theta and their magnitude. So for A, we decompose it into A cosine theta, A sine theta. And for B, we decompose it into B cosine theta, B sine theta, and just add those corresponding coordinates. And we end up getting the vector sum. Okay, and all of this so far has been vectors in 2 dimensions, but we can do vectors in 3 dimensions in exactly the same way. It's just that now we have a third coordinate. So vector addition, vector scaling, all work the same way. Vector addition, you just add the corresponding x, y, and z coordinates, where z is the third dimension, illustrated here. We imagine the z-axis as being orthogonal to the x and y axes. So, for example, this vector ABC would have components, well, a comma b comma c, which correspond to the x, y, and z coordinates of the vector respectively. And to geometrically add, well, this is what I said about vector addition, to geometrically add vectors in 3 space, you just move one vector still so that its tail is at the head of the other, and everything works identically. So in other words, this definition still holds. Just imagine now that u and v are vectors in 3 dimensions, and it still forms a parallelogram, and the vector sum is still geometrically the diagonal of that parallelogram. And how do we find the magnitude of a vector in 3 dimensions? I encourage you to pause this video and try to think of how, and I'll show you in a bit. Okay, so I'll illustrate with an example. So here's a vector 2, 4, 1. So that means 2 in the x direction, 4 in the y direction, and then we go up 1 in the z direction. So that's our vector, and how do we find its length? Here is an illustration. So how we can find its length is to first find this length, and that's a length in 2 dimensions. We know that the length of that is, by our previous definition of length using the Pythagorean theorem, the square root of the difference in the x coordinate squared plus the difference in the y coordinate squared. And then to find this length, well, we recognize that this is also a right triangle. So we take this length and square it, plus that length and square it. And that's what this here says. And then we add those together and take the square root. Well, this guy here squared gets us that. So this is our a squared, and then our difference in the z coordinates is our b squared. So that's our square root of a squared plus b squared in the yellow triangle here. So in other words, the square root of the sum of the squares generalizes, and the general formula for the magnitude of a vector is the square root of the sum of the squares of its x, y, and z coordinate differences. Now, a unit vector is a vector of length 1. 1 is in general called the unit. And being of length 1, well, length is just another word for magnitude. And this is therefore saying that the magnitude of the vector v is 1. And unit vectors are mathematically useful for encoding a pure direction by itself. And given a vector v, the unit vector in the direction of v is, how can we think about this? Well, we can take our vector v that might not be of unit length, and if we take our vector v and divide it by the magnitude of v, then we take v. Let's imagine that here the magnitude of v is 3. So then v over the magnitude of v will be v scaled back by a factor of 3, and then this guy will be of magnitude 1. And this v over the magnitude of v is therefore the general formula for converting or finding the unit vector that's in the same direction of a vector v. So we have that the unit vector in the direction of v is v over the magnitude of v. So just to illustrate, what is the unit vector in the direction of 3i plus 4j? Well, first recall that 3i plus 4j is the same in our other system for denoting vectors as 3, 4. That's just the x and y coordinates. And we want v over the magnitude of v. So that's 3, 4 over the magnitude of 3, 4. Well, the magnitude of 3, 4 is, by the Pythagorean theorem, the square root of the sum of the squares of the components. So that's the square root of 3 squared plus 4 squared. And 3 squared plus 4 squared is 9 plus 16 is 25. And the square root of 25 is 5. So we have 3, 4 over 5. Just to be clear, this is the same as 1/5 times 3, 4. And vector scaling works by distributing the scaling factor to both coordinates. So the unit vector in the same direction as 3, 4 is therefore 3/5, 4/5. This is a list of properties of vector operations. These axioms are what in general define a vector space, but that's a topic for linear algebra. And in this course, we're just using the basics of linear algebra and won't get into the full breadth of what these entail. So vector addition is commutative. Remember that commutative means that you can swap the order and you get the same result. So u plus v is v plus u. Vector addition is associative. Associative means that we don't care about order of operations, essentially. So u plus v plus w is the same as u plus v plus w. So this means that in practice, we can just omit the parentheses and write u plus v plus w. No need for parentheses. The zero vector plus any vector is that other vector, and any vector plus its negative is zero. Vector addition, well, and scaling is distributive. So c plus u plus v, we can distribute that c to both components, and we get cu plus cv. And is also distributive in the other way. A plus c, where a and c are scalars, is the same as av plus cv. Any vector times zero is the zero vector. And notice that they make a distinction here between the number zero and the vector zero with a ordinary versus bold distinction. If you take the zero vector and multiply by a constant, well, it's still zero. Any vector times one, you distribute the one to all components, and it doesn't change anything. You get back v. And also vector multiplication by scalars is associative, which means that, again, you don't need parentheses. You could just write this as ACV. So all of these make vectors behave as you would hope they behave, and you don't need to remember this list. You just need to, well, apply the same things that you know from dealing with ordinary numbers to vectors, and everything carries over. So here's a true-false. Given a non-zero vector v, there is only one vector parallel to v. Is that true or false? Take a moment to think about that. So let's visualize this. Here is a vector v. Can we imagine more than one vector parallel to v? Remember that two vectors are parallel if one is a scalar multiple of the other. So maybe we can imagine 2v, that's parallel. Or, and then we can also maybe imagine, well, 3v or negative v. So 3v is also parallel, and that's two distinct vectors, both of which are parallel. So this is very false. And remember that we could also go in the negative direction. So that's negative v, that's also parallel. Problem. Another example problem. I tried to make the problem similar to the homework. Find a vector in the direction of 5, 12 of length 3. Again, I encourage you to pause the video, try to work this out. Mathematics is like learning how to swim. You can't learn how to swim by watching someone else swim. You need to go in and struggle and try yourself. So how can we think about this? Well, we know how to make a unit vector in the same direction of a given vector. We know that v over the magnitude of v is a unit vector in the same direction. So let's visualize this. We have some vector v. We can make or find a unit vector. So let's imagine that that's v over the magnitude of v, which is therefore of length 1 being a unit vector. And then we can take that vector of length 1 and scale it by a factor of 3. So from there, we can scale it by a factor of 3. So that vector there would be 3 times v over the magnitude of v. And that is therefore of length 3. So what we want to compute, therefore, is 3 times v over the magnitude of v. And as you can see from this, this is why I always emphasize the geometric understanding of vectors, and in general, a geometric understanding of mathematics is how we really want to think about it, and everything algebraic just corresponds to what's really going on geometrically. So we want to compute 3 times v over the magnitude of v. So that's 3 times 512 over the magnitude is the square root of the sum of the squares, so that's 5 squared plus 12 squared. is 25 plus 144 is 169. Square root of 169 is 13. So we have 3 over 13 times 512 is 15 over 13, comma, 12 times 3 is 36 over 13. Is a vector of magnitude 3 in the same direction as 512. Now, we begin our introduction to equations in 3 dimensions. Oh, in case I didn't mention this symbol here. So first, this very fancy looking R denotes the real number line. And this superscript 3 means that we want to imagine the real number line kind of multiplied by itself 3 times, which gets us 3 dimensions. So to be clear, that means that R2 is the Cartesian plane, and R3 is 3D space, like the 3D Cartesian plane. What's denoted here in these diagrams with our orthogonal x, y, and z axes. So the equation x equals 2 means the set of all points with x coordinate 2. In 2 dimensions, that's a line, as you know, and in 3 dimensions, well, it's a plane, because every point on this plane has, as you can see, x coordinate 2. It doesn't matter what y or z is, so long as the x coordinate is 2. Similarly, x equals 0 means the yz axis, because the yz axis, well, x is 0 everywhere there. Similarly, for y equals 4, everywhere here, the y coordinate is 4, or z equals 3. Everywhere there, the z coordinate is 3. And again, similarly, so x equals 0 is the yz axis, y equals 0 is the xz axis, and z equals 0 is the xy axis. And our first non-trivial equation in 3 dimensions is the equation of a sphere. So a sphere centered at the point ABC with radius r is the set of all points satisfying this equation. Okay, before we look at this equation, let's imagine a sphere. I can't draw a sphere, so let's imagine a circle. There is our center. So everywhere on this circle, that means that we are of distance r away from the center for every point, distance r. So in other words, a circle is a set of all points of distance r from its center. And similarly for a sphere is a set of all points of distance r from its center, just in 3 dimensions. So how do we get that? Well, a given point xyz being of distance r from its center ABC means that the magnitude of the vector from ABC to xyz is r. So the vector from the center ABC to a given point on the sphere xyz is the difference of the 2 vectors, which is x minus a, comma y minus b, comma z minus b, subtracting the corresponding coordinates. And the magnitude of that is the square root of the sum of the squares of the components. And we want the magnitude of the difference of a given point on the sphere to its center to always be r. So you just take this equation, therefore, and square both sides. And then squaring both sides gets rid of the square root on the left and makes that r on the right r squared. And we wind up with this. So that is our equation of a sphere of radius r centered at ABC. And a ball just means a filled-in sphere, so the set of all points on the sphere itself and everything inside of it. And that means that the magnitude of a point from the center is less than or equal to r, and then squaring both sides, that's less than or equal to r squared. Sometimes the equations of, say, spheres are not immediately in that form that we want, and we need to get them in that form. So describe the shape given by this equation. As you can infer, we've only really learned one type of equation so far, and it's a sphere. So you can reasonably infer that this is the equation of some kind of sphere. But why? How? Our equation of the sphere looks like this. It doesn't have any x or y by itself. But this guy has an x and y. So what's going on there? If you want, take a moment and pause and take more than a moment to try to figure it out. So we have an x squared and a 2x, for example, and we want to get that to look like x minus a squared. Well, if we take x minus a squared and FOIL it out, we have x squared minus 2ax plus a squared. So FOILing this guy out, we end up with, in fact, an x component that is not squared. And the opposite of FOILing that out is completing the square. So what we want to do is complete the square for each of these components. So let's remember how to complete the square. So x squared plus ax, we can think of it this way. We are going to add an a over 2 squared and subtract an a over 2 squared. And the combination of these two means that we are doing nothing in a fancy way. And if there's one thing mathematicians are good at, it's doing nothing in a fancy way. Kidding. Okay, but this first component here is this. And you can see that by FOILing this out. FOILing this out, we have x squared plus 2a over 2x, which is just ax, plus a over 2 squared is that guy. And then this guy is still hanging out on the outside. So that is the process for completing the square. And you could just memorize that that's the completed square form, but I'm not good at memorizing. But one good nice thing about mathematics is you don't have to memorize if you understand what you're doing and where it comes from. So every time I complete the square, personally, I have to think of this, and then I get that. So let's complete the square here and see what happens. So again, for each component. So gathering together terms, by which I mean gathering together the x terms, y terms, and z terms, we have x squared plus 2x plus y squared minus 4y plus z squared plus 6z. And that minus 2, let's move that to the other side. So adding 2 to both sides, we have equal to. Now, that's a. We want to add and subtract a over 2 squared. Okay, so a over 2 is 1. So we want to add 1 and then subtract 1. That's our doing nothing in a fancy way. That will allow us to complete the square. This guy, if we factor it, is x plus 1 squared. Okay, similarly for this guy, we're going to add a over 2 squared. A over 2 is negative 2. Negative 2 squared is 4. And subtract 4. And so a over 2 squared is 3 squared is 9. So we'll add and subtract 9. And to be more clear about what we end up factoring, we're factoring each of these guys in the yellow parentheses. Okay, so that first yellow parentheses, factoring that, we have x plus 1 squared, so that minus 1 hanging out, plus y minus 2 squared, so that minus 4 hanging out, plus z plus 3 squared, and still that minus 9 hanging out is equal to that original 2 that we added to both sides. And now finally, we'll gather all the constants on the other side, and doing so, we'll get it into our desired form of a sphere, from which we can then identify its center and its radius. So now we want to express this in the given form of a sphere. So let's move the constants to the other side. So minus 1 minus 4 is negative 5, minus 9 is negative 14, and we add 14 to both sides, and we have equals 16. So now we have x plus 1 squared plus y minus 2 squared plus z plus 3 squared is equal to 16. Now, this is almost in the form of a sphere. However, recall that the form of a sphere had x minus a squared, but we have an x plus 1 squared. So what can we do about that? Well, x plus 1 is x minus -1. So let's rewrite this as x minus -1 squared. Y minus 2 is already fine. And z plus 3 is z minus -3 squared. And we want equals to r squared. And 16 is the same as 4 squared. And our general form of the sphere centered at ABC of radius r was x minus a squared plus y minus b squared plus z minus c squared is equal to r squared. So that is our a, b, and c, and r. And therefore, this is a sphere centered at -1 to -3 of radius 4. So we have figured out what shape in R3, three-dimensional space, this equation corresponds to. And that concludes this lecture on chapters 13.1 to 13.2.